Hello everyone. On this video we will be going over directional angles and projections involving the dot product, or the use of the dot product. Okay, so first let's take a look at what we mean by a directional angle. Alright, so first we're going to draw our three-dimensional space. You have your Z, then your X, and your Y axis. Again, if you want to picture it in your mind, picture the corner of a room where this is the left wall, this is the right wall, and this is the floor. Okay, so imagine that starting right in the corner, you have a ball in your hand, and you walk 1 foot, 1 yard, whatever way you want to say it, but you walk 1 unit along that wall. Okay, so if you have, better yet, imagine a ball in your hand. You roll that ball out 1 unit, like I say, it could be a foot, could be a yard. And let's say that once you get to that spot, you roll that ball out the same direction as the Y wall. Okay. Okay, so you rolled it 1 yard this way and 1 yard that way, where you're right there right now. Okay. Now imagine that ball, you are now lifting it up in the air. Okay, so if you lift that ball straight up into the air to where it is now here. Okay, so what we're doing now, we're going up that Z-axis. Okay, now you get a stick and you put it between the ball and the corner. That stick would be your vector. Okay, we'll call that vector A. Okay, which leads from the corner right to that stick. And we have all the measurements to see exactly where that ball is. Okay, now with directional angles, what we're doing is, let's say if we wanted to decide the angle between the corner of the left wall and that vector, or in that stick. Okay, that'll be angle alpha. But what if we wanted to decide the angle, or find the angle between the right wall and that stick, or the corner of that right wall and the stick? That would be our beta. Or even if we wanted to find the angle between going up the wall and that stick. I'll move this. Let me move this alpha over a little bit. A vector over a little. This would be angle gamma. Okay, now in this case, our alpha, beta, and gamma are what we call directional angles. Okay, now if we have what we call cosine of alpha, cosine of beta, and cosine of whatever gamma happens to be, those are called directional cosines of our vector A. All right. Now, you just remember that cosine of whatever angle, we'll call it angle theta, equals adjacent over the hypotenuse. Okay, now using that, you can say that cosine of alpha, remember alpha's from this corner of the left wall to the stick, that we just look at this shading here, that would be the adjacent, which is however long this is. It doesn't have to just be one. I just use that kind of as a guide. So whatever length this is, this would be adjacent over the hypotenuse, which is the length of your vector. Okay, so that's going to equal however long that x value is, which we'll call a1, over the length of our hypotenuse, which is the magnitude of a. Okay, where alpha equals the angle between our vector and our unit vector that we use here. Again, like I said, this could be, x value could be any length at all. I just happen to use unit vector for these examples. But if this had a length of 20, it would be the same thing between a and whatever length that is. Okay, now what if we had our cosine of beta? Okay, that's equal to our second component divided by the magnitude of the vector. Of course, in this case, beta is equal to the angle between our vector A, and our J vector. All right, now what if we had cosine of gamma? Of course, that would equal, make that a little clearer, our third component divided by the length of our A vector, where of course gamma is equal to the angle between our A vector and our K vector. All right. Now, just a little tidbit of information here. Any non-zero vector that we'll call A in space, be 2D or 3D, has a normalized form. Okay, so that means that our A vector divided by the magnitude of A can actually equal, that over a little, our first component divided by the magnitude of A times the I vector, plus our second component times the magnitude of A times the J vector, plus the third component divided by the magnitude of A times the K unit vector, which, since that's A1 over A is cosine of alpha, I'm glad I caught that little error. That should be alpha. There you go. Sorry about that if it confused you in any way. Okay, so we have cosine of alpha times the I vector plus cosine of beta times the J vector plus cosine of gamma times the K vector. Okay, so that's our normalized form. Okay, and a last note on this page. Our cosine squared, why do I keep confusing my alphas and my gammas? Alpha plus cosine squared beta plus cosine squared gamma is actually equal to 1. All right. So if you are still writing, feel free to press pause. But we're going to go ahead and go to our next page, which will prove that these three formulas are exactly the case. Okay, so our direction, cosine, proof. Okay, so let's say if we have our three-dimensional corner again. So we have x, our y, our z. Okay, so let's say this isn't a unit vector. Let's say this goes out to some value of x. Okay, so this goes out to some point x, 0, 0. Okay, it could be 2, 3, 4, 20, 100. It just goes out to that value. Okay, so just like before, we have our x, then we roll it up some length y, where it meets there, and then it goes right up in the air. And to that point, that's where our vector, we'll call it v. Well, we'll call it a just to keep it uniform. Okay, now at this point, this is our point, x value, y value, and z value. Okay, so we're going to pay attention to just this portion of it. Okay, we're going to forget that part. We're going to pay attention to just this portion. So if we pay attention to just this portion, kind of looks like, let me straighten up my value here. There we go. Kind of looks like this, where this is the length of our vector A. Remember, you have your alpha, which is the angle between this wall and the vector. So that's alpha. And this is the length of our x. Okay, so that's shaded in area. I just kind of moved it over. We extend this a little bit so I can have my vertical line. There we go. So it kind of looks like that if you get that shaded area and move it over here. Okay, so we see that cosine of alpha is equal to adjacent over the hypotenuse, okay, which is equal to whatever your x value is over the length of your vector. Okay, so here, our x value is some value we will call a1. So our cosine of alpha equals a1 over the length of vector A. All right, so it'll be the same thing for beta and gamma. All right, so the proof of that one is pretty straightforward. All right, so if you are still writing, feel free to press pause, but we're going to jump into our first example. All right, so let's say, for example, find the direction, cosines, and angles. This time we're going to go in degrees. Remember, sometimes they'll ask for it in radians, sometimes they'll ask for it in degrees. You have to be aware of your calculator settings because they can bounce back and forth depending on the problem. For the vector, okay, so a vector equals 3 times the I vector plus 2 times the J vector minus 2 times the K vector. Okay, and show that cosine squared alpha plus cosine squared beta plus cosine squared gamma equals 1. And we want to round to 1 decimal place. Or your nearest 10. Okay. Sometimes they may ask you to round to the nearest degree. It all depends on the question. All right. So we can figure out that the magnitude of the A vector is equal to the sum of each of the component squares. So you have 3 squared plus 2 squared plus negative 2 squared. Okay, so 3 squared plus 2 squared plus negative 2 squared. Okay, so you have 9 plus 4, 13 plus 4, 17. You have the square root of 17. Okay, so that's our magnitude. You know that cosine of alpha is our first component divided by the magnitude of the vector. Okay, so that's 3 divided by square root of 17. Okay, so cosine alpha equals 3 over square root of 17, which means that alpha is equal to the cosine inverse of 3 over square root of 17. So if you plug that into your calculator, you will get 43.3 degrees, which of course is the angle between the A vector that they gave us and our I unit vector. Okay, so we have our directional cosine and our angle. Okay, so we do the same thing for cosine of beta. That's equal to the second component divided by the magnitude of the vector. Okay, so our second component is 2. That's 2 divided by square root of 17. Okay, so we know here that cosine of beta is equal to 2 over square root of 17, which is our directional cosine. Oh, that should be directional cosine. There. Okay, but if we apply cosine inverse to both sides, that means that beta is equal to the cosine inverse of 2 over square root of 17. And that comes out to about 61 degrees, okay, which is your angle between beta and, oops, not beta, your A vector and J. Sorry about that. Okay, So again, your directional cosine and your angle. Okay, so how about cosine of gamma? All right, so what I want you to do is I want you to press pause and do the cosine of gamma on your own. All right, so assuming that you've already pressed pause and worked this one out, we know that cosine of gamma is equal to our third component over the magnitude of A, okay, which is -2. Oh, move that down. There we go. -2 over square root of 17. Okay, so we know that cosine of gamma is equal to -2 over square root of 17. That's our directional cosine. Apply cosine inverse to both sides. We know that gamma is equal to the cosine inverse of -2 over square root of 17, which comes out to about 119 degrees. Okay, which of course is the angle between our A vector and our K unit vector. Okay, so we solve for our directional cosines and our angles. But we still have to verify that the square of each of our directional cosines is equal to 1. All right, so we want to see that cosine squared of alpha plus cosine squared of beta plus cosine squared of gamma. Okay, so our cosine alpha is 3 over square root of 17, so that's 3 over square root of 17 squared. Plus our cosine beta is 2 over square root of 17, so that's 2 over square root of 17 squared. Plus our cosine of gamma is -2 over square root of 17, so that's -2 over square root of 17 squared. Okay, so 3 squared is equal to 9 over square root of 17 squared is 17, plus 2 squared is 4 over square root of 17 squared, which is 17, plus -2 squared is 4, and that's again over 17. 9, 13, 17, so we have 17 over 17, which is equal to 1. Okay, so we have just verified that the sum of all of those directional angles squared is equal to 1. All right, so if you are still writing, feel free to press pause, but we're going to go ahead and move on. All right, so let's say we start on projections. Okay, so for our projections, what if we let A and B represent non-zero vectors? Uh-oh. There we go. All right. So let's say if we start drawing our vectors here. Okay, so let's say this is vector B, and let's say that this is vector A. Okay, Now this vector, this vertical vector here, we'll call that vector W2. Okay. Now vector A, what we're looking right here at the tip of vector A. Okay. So let's say we want to create another vector that's right up under there with vector A. Okay, so we're going to kind of go on top of vector B and stretch it all the way out here. And we'll make that a dotted line just to distinguish it from our B vector. All right, so this entire length, we'll call that vector W1. Okay, now if we get our vector W1 and we move that right up here, remember our vector can be moved all over as long as it's the same length and direction, it's equivalent. So this is our W1 vector here. This one we just moved right on up. So we see here that vector A is equal to vector W1 plus W2. Okay. So really what that gives us is that vector W1 is equal to some constant times vector B. So they're parallel, and this is just the same direction and length. It's just, well, same direction, but it's just longer. And we also see that the dot product of vector W2 and vector B is equal to 0. How do we know that? Because 90-degree angle. Remember, two 90-degree vectors are orthogonal. All right, so what we want to do is we want to find the length of vector A. What length would vector A have to be right over vector B? Okay, we know what it would have to be in order to cover that whole vector of W1. We want to know that if this is some theta, how long or how far up vector A will we have to go right over vector B? Okay, so if we start off with our cosine of theta equals the dot product of A and B over the magnitude of A times the magnitude of B. Okay, so just starting there. Okay, so if we multiply both sides by the magnitude of A and B, we have the magnitude, we'll put the B first, times the magnitude of A times cosine theta equals the dot product of A and B vector. Okay, now what if we just divide both sides by the magnitude of B? Okay, so we have the magnitude of A vector times cosine of theta equals the dot product of the A and B vector divided by the length or magnitude of the B vector. Okay, now this right here would actually, let me turn that, there we go, will actually give us the magnitude of the vector projection. Okay, now the projection here is really, you can kind of think of it, which I always love this comparison, think of it like a shadow. How long would this have to be if you had a sun directly up top for the shadow to stop right at the B vector? So this right here would give us the magnitude of the vector projection. Okay, so since that's the case, what they did was they gave this its very own name. So you have the component of vector A right here onto vector B is equal to the dot product of the A and B vectors divided by the magnitude of the B vectors. Okay, so what this is called, let me kind of separate this a little bit so you don't confuse those two. So giving that a little more room. This is the scalar projection of vector A onto vector B, or depending on the textbook you're using, component of vector A along vector B. Okay, so both of them would be basically the same thing, just different names. All right, so that's your scalar component. But let's look at the actual projection. All right, so if you're still writing, feel free to press pause, but we're going to go ahead and move on to our next page. Okay, now the one thing we know is that we need magnitude and direction for a directional vector, or a direction vector. Okay. Now the thing is, we can just use our scalar component we just figured out as our magnitude, and we just need a vector in the same direction as our B vector. Okay, so if you remember, you have the scalar component of A onto B times a unit vector in this, or vector in the same direction as B. Okay, so here you have your scalar multiple. The same direction as vector B. Okay, so really all this simplifies to, since we figured out our component on the previous page, that's the dot product of A and B over the magnitude, why do I keep wanting to put A here, of B times vector B over the magnitude of B. So if I finish that one off. Okay, now what if we just go ahead and multiply these two together, just for simplicity? So we have the dot product of our A and B vector divided by the length of the magnitude squared, and all of that times our B vector. Okay, so all we did was move that over, multiply those two, and leave our B vector out here. This gives us our vector projection of A onto B. Equal to the dot product A and B over the magnitude of B squared, and all that times our B vector. Vector projection of A onto vector B. Okay, so it's just a slight change between the two formulas. All right, so what are our general equations? In general, we have our scalar component of our A vector onto our B vector. Is scalar component of our A vector onto our B vector, which is the dot product of the A and B vector divided by the length of the B vector. But it doesn't have to appear in that form. You could have the scalar component of the B vector onto the A vector. Okay, so the scalar component of our B vector onto our A vector is still the dot product of the A and B vectors divided by the magnitude of the A vector this time. Okay, so if it's A onto B, our B vector, the magnitude of the B vector is in the denominator. If it's B onto A, the magnitude of the A vector is in the denominator. Okay, so you can see here A onto B, B onto A. So that hopefully helps you remember how to set it up. And it's the same thing with the vector projection. Okay, so if we have the vector projection of A onto B, okay, so that's the scalar projection of A onto B is equal to the dot product of the A and B vector divided by the magnitude of the B vector squared times your B vector. And or you can put it this way. Scalar component, put that underneath it since I'm running out of room here. The scalar component of A onto B times the B vector divided by the magnitude of the B vector squared. Okay, so you can use either one of those. Because really all this is this version down here is just that. All right, and one more. We have the, running out of room here, trying to squeeze it all on this page, vector projection of B onto A. That is just the scalar projection of B onto A vector equals the dot product of the A and B vector over the magnitude of the A vector squared times the A vector, or it can also equal the scalar component of B onto A times our A vector divided by the length or magnitude of the A vector. Oh, actually this is not squared. I don't know why I did that. Okay, so be aware that this second one isn't squared. That was just an error on my part. Okay, so if you have these four formulas, it will be all set for your projections. All right. So if you are still writing, feel free to press pause, but we're going to go ahead and jump into one of our examples. That over, there we go. Okay, so let's say, for example, if we want to find the scalar and vector projection of B onto A, let's say that our A vector is equal to -2, 3, -6, and our B vector is equal to 5, -1, 4. Okay, so we have our A vector and our B vector. And it's the exact same thing for 2 dimensions, so no changes there. All right, so our scalar component of B onto A equals the dot product of A and B divided by, remember when it's onto A, that means the magnitude of A is in your denominator. Okay, so the dot product of A and B, we multiply the first 2 components. So it's -2 times 5, plus you multiply the second component, 3 and -1. You multiply the third component, -6 and 4, divided by the magnitude of the A vector is -2 squared plus 3 squared plus -6 squared. Okay, so we end up with -10 minus 3 minus 24 over square root of 4 plus 9 plus 36, which is equal to -37 over 7. Okay, which is our scalar component. Okay, so now we use that to find our projection, vector projection of B onto A. Okay, remember, you can use one of 2 formulas for this. Okay, if you wanted to, you could say the dot product of the A and B vector divided by the magnitude of A squared times the vector A, or the scalar component of B onto A times the vector A over the magnitude of A. Here we already figured out the scalar component, so we might as well use it. So that's going to equal -37. That actually should be 37 over 7. I'm actually, there we go, times our vector A over magnitude of A. So that's our vector A. So that's -2, bring that down a little bit, 3, -6, all over our magnitude of A, which we've already figured out is equal to 7. Let me clean up that 3. That's been bugging me for a second there. There we go. Okay, so if you multiply the 2 7s, that's going to equal -37 over 49 times your A vector, -2, 3, -6. And since you have a scalar times your vector, you just go ahead and multiply those. So you have the vector 74 over 49 negative 111 over 49, and 222 over 49. This is our vector projection of B onto vector A. All right. So if you are still writing, feel free to press pause. But we're going to have one more thing to go over, and that is our definition of work. Our definition of work. Okay. Now, I guess you could say the simplified definition of work, which we will identify as the uppercase W, is mainly described as the constant force, which we'll call our F vector, moving along a line of motion. Okay, so if we put that into a definition, work would equal the magnitude of force times distance. Or work is equal to the magnitude of force times distance from, let's say, from some point P to point Q. Again, we don't use the dot there for multiplication because we have a dot product, so we just have those next to each other as multiplication. Okay, so if we wanted to kind of draw this out, and we have two objects here. Let's say we have some point P. We wanted to drag this to some point Q. So this is just moving all the way there. We could have some straight line force moving it. And really, this is just force acting on a straight line. Okay, so in this case, work is equal to the magnitude of force times the distance from P to Q. But what if you're not moving just along a straight line? Okay, what if your force is at an angle? Okay, so if we have that same straight line, that same object, and go ahead and shade that in. And again, we're going to move that object from point P to point Q. But we're not moving that straight line. What if our force is moving at an angle? Okay, which is a certain number of degrees or radians from that straight line. This would be your force not directed along a line of motion. All right. Okay, so here in this case, our work will be equal to the magnitude of the scalar projection of the force along the line from P to Q. times the distance, which is the magnitude from P to Q. Okay. So really, we could rewrite this as work is equal to cosine of theta times the magnitude of force times the distance from P to Q. Or work is equal to the dot product of force and distance. Or in the vector, not distance. Okay? So really, you can probably stick to just those two. Where this is the projection form of work. And this is the dot product form. Of work. All right. So if you are still writing, feel free to press pause. But we're going to go ahead and do a quick example of this. All right, so let's say for our example, a tow truck drags a stalled car along a road. Okay, so let's say the chain makes an angle of 30 degrees. Angle of 30 degrees. With the road and tension on the chain is 1,500 newtons. Okay, so how much work is done by the car, by the truck pulling the car for 1,000 meters? All right, so to solve this one, we know that the distance from point P to Q is 1,000 meters. Our angle is 30 degrees, and the magnitude of the force is 1,500 newtons. Okay, so work, which is of course the dot product of the force and the distance. Since we have an angle thrown in there, we'll use this form. Cosine theta times the magnitude of force times the magnitude of the distance. Okay, so we have cosine of 30 degrees times 1,500 times 1,000. Okay, so we have square root of 3 over 2, our cosine of 30, times our 1,500 times 1,000, which ends up being 750,000 times square root of 3 joules. Now, this particular question didn't ask us to round to the nearest tenth, hundredth, thousands, or anything like that, so we're just going to leave it as an exact value. All right. So hopefully this video made sense to you, and I will see you on the next video.